and then basics of rheology. And these are Stokesian, suspensions. So they obey Stokes' law. So we build solution, Stokes solution for a single particle and then go for the multi-particle system. And then how the solution for a single particle can be built to incorporate many body hydrodynamic interactions through multiple expansion. And then, the details of how do we carry it out Stokesian dynamic simulation to compute the rheology of suspension. And then some example that we can not only study the Newtonian one, we can also study shear thinning and shear thickening suspension. So it's slide visible. Can you see the slide changing?
Yes, sir.
Okay.
No, sir, it is not changing.
Yeah. So coming to suspension,
Yes, now it is
uh, you see there are plenty of example, okay, in day-to-day life, right from food product, chocolate, you have milk, okay, and then industrial like paints you have, okay, daily use toothpaste. Even our blood is a suspension of solid particle in liquid medium. Then of course in nature also we see you have slurry transport or sediment transport in river. So though suspension is basically dispersion of one phase into other, but we in this case talk what we refer is that the solid particles in liquid media. Okay? And again, you can change particle, you can change liquid, and you can have various types of suspension. So if the particles are same size, we have monodisperse. We can also have polydisperse. And broadly, depending on size, okay, you can have homogeneous, okay, where the particles, okay, size is typically less than 1 nanometer. You can have colloidal, okay, between one nanometer and 1 micrometer, and non-colloidal greater than 1 micrometer. Right. Another example, okay, is your drilling fluid. While drilling, okay, oil well, we use drilling fluid, which is a suspension of bentonite, okay, in either oil or water. Okay, so mostly water based, okay, bentonite mud is mostly used. So there are plenty of example, and okay, we will see that whether we can compute the rheology of especially non-colloidal. Colloidal also it's easy. You have to add the interparticle forces. So once you have a framework for the non-colloidal, we can easily add the contact or any other interparticle forces to also simulate for the colloidal one. Now we know that how do we compute rheology, in experiment. So basically, okay, we apply shear, okay, and let's say you have a simple shear where bottom plate is stationary and top one is moving, right? So shear is created, steady shear. So material, okay, this material is being deformed. Of course, when we deform, stresses will be generated in this, okay, or otherwise to deform it, okay, you need to apply some forces, okay, and force per unit is your stress. So your stress, okay, is proportional to the rate of deformation or velocity gradient in this case. So most of K in the experiments, either we have cylindrical cuvette where you have inner cylinder and then outer cylinder, right? And you put the material in the gap between the two, or you will have cone and plate where you put your suspension between a rotating cone and a stationary plate, and you measure the torque. And the torque you can know the stresses, or you have a parallel plate where the top plate is moving rotating at certain rate and the bottom is stationary, and you put your material between the two plates. So all these are example, and the gaps are such that the shear rate is constant. So all these are example of planar shear, right? So you can okay, have one component of velocity gradient and you measure the stresses, and the proportionality constant is, let's say, viscosity. So viscosity is just one rheological property, dynamic viscosity. Now, if you have deformation, okay, in 3D, right? So in 3D, what you'll have, okay? So this is just a one component where you have deformation, okay, in one direction, and then you have the stresses, right? So this tau actually you can call tau ix, where x is the flow direction and y is the gradient direction, right? But if you have 3D flow, then you will have how many components? Stress is force per unit area, right? Okay. So stress you need, okay, let's say on this surface, right? So force per unit area, and area itself is a vector with a magnitude, and you have direction, okay, normal, outward normal. Okay. So you need, three in Cartesian coordinate, you have three component of forces and three for the area vector, nine. So that's why you have the stress tensor have nine component. Again, for the fluid system, you can break into isotropic part, that is pressure, and this is the viscous part. This will be there even if there is no deformation, the isotropic, the pressure part, right? But this part of the stress tensor arises only when you deform. Okay, as you can see that this you can clearly make out these are the symmetric part, because we'll see later is the symmetric part of the velocity gradient tensor, which basically generates your viscous stresses, right? So in the conventional notation, you can write pi, I is the identity matrix, plus mu times grad u plus grad u transpose. And what is grad u? Grad u is the velocity gradient. It's not del dot u, right? Grad u, see, this is a vector, this is a vector. So again, it has nine component, right? So these you will have nine components. These are the nine component. Okay. So it's a called second order tensor, right? So this is also second order tensor, right? And we know that half of, okay, this E is, okay, symmetric tensor, symmetric velocity is half of grad u plus this transpose, right? This is called the symmetric part of rate of deformation tensor. That is responsible for the viscous stresses I told. So this you can write as the sigma, okay, is equal to minus pi plus 2 mu e. Can you see annotation on the slide? I am using a marker. Can you see?
Yes, sir, is visible.
Yes, sir.
Yes, sir.
Okay, good, good. Yeah. So in 3D, actually, you will have to relate, right? You'll have to relate stresses to the velocity gradient tensor, right? And when you do computation, okay, in 3D, it becomes, even more challenging, because you will have to, relate not only various component, you'll have various kind of interaction between multiple particles. But this is all about, once you can compute, okay, this relation, you can compute the rheology. Okay, now coming to the velocity gradient tensor, right? So let's say, okay, you have velocity gradient grad u, right? Also in initial notation, it is written as del z ui. Okay, this is very useful, Einstein notation. So basically, I and j are the, two indices for the direction, right? So j is for the, okay, indices for the gradient direction, and u is for the velocity vector. So again, ij, you'll have nine component, right? So you can write del u1 if you write 1, 2, 3, or x, y, z, whatever. Okay, del u1 by del x1, del u1 by del x2, del u1 by del x3, and del u2 by del x1, del u2 by del x2, del u2 by del x3, and del u3 by del x1, del u3 by del x2, del u3 by del x3. These are the nine components. And again, we know this is a matrix, right? Okay, 3 by 3 matrix, and any matrix we know that we can write, okay, as, okay, symmetric, okay, plus antisymmetric part, right? So if A is the matrix, its symmetric part is half of Aij plus its transport Aji. Antisymmetric part is half of Aij minus Aji. Okay. And okay, if you read any fluid mechanics book, you will see that the antisymmetric part of this velocity gradient tensor, right, is basically responsible for the solid body rotation, right? Complete rotation. No relative deformation. Okay. and the symmetric part, right? So this is related to your Wij antisymmetric part. The symmetric part is related to the deformation or the shear, okay, where you'll have relative velocity gradient, a velocity difference between the two layers. And the isotropic, this the diagonal part. These are the diagonal part, right? So diagonal part are responsible for expansion or contraction, right? Okay. So the trace of this will be what? Okay, the trace will be 1/3 of, okay, sum of diagonal part. And if you can note, the sum of diagonal part are nothing but del dot u. And if it is incompressible, del dot u is 0. That means there is no net expansion or contraction of the, okay, fluid volume, right? So what will be important is, yes, there will be Wij, antisymmetric part and symmetric part. So rigid body rotation does not cause deformation, right? Your whole body is rotating like a solid disk or solid body, right? Only when you have a shear flow, there will be deformation, and then viscous stresses will be generated. So viscous stresses are, okay, proportional to Sij. They depend on Sij, symmetric part. Okay, and okay, we all know that, okay, the viscous stress. This is the viscous stress. Viscous stress. Viscous stress is mu into, okay, grad u plus grad u transpose, okay, or you can write 2 mu plus, okay, half of that, that's the Eij, both are same thing. Then this becomes your symmetric part of the velocity gradient tensor this time. Minus, you can see, right? This is what? The trace, okay? 1/3 is the trace. So 2 mu you can take constant. So this is nothing but this part, right? The trace part. Why this is there? Because we have not specified. If there is a compressible fluid, this component also will be there. That means, okay, there will be stresses generated due to expansion and contraction. But if your fluid is incompressible, this term will be 0 for incompressible. Okay, right? So you becomes your viscous stress simply mu times grad u and its transport. Okay. So we should relate, okay, tau ij to this rate of deformation tensor. Okay. And coming to, what kind of behavior we obtain, especially the, in terms of viscosity, we all know this is the standard curve. Okay. So if you plot shear stress versus shear rate, right? This is a Newtonian. That means the shear stress is directly proportional to the shear rate. In this case, the slope is decreasing. That means what? Slope is the viscosity, right? Here the slope is constant. That means it's a Newtonian. Mu is constant. Mu is equal to constant. Here what? The slope is decreasing. That means it's shear thinning. That means it's becoming less and less. Slope decreasing, mu decreasing. That means less and viscous. So this is shear thinning. Opposite is shear thickening or dilating. You can also have some, material like toothpaste where you need to basically apply certain yield stress, then only it will start flowing. Okay, so this will be your yield stress. You'll have Bingham plastic, or you can have Bingham pseudoplastic if it has yield stress and also shear thinning. Most of the toothpaste ketchups, they will be Bingham pseudoplastic. Okay. Again, there are other class where, okay, these are at, constant shear, right? These different point, or okay, you plot the data at constant shear. There are also materials which are time dependent. We will not discuss time dependent, okay, like viscoelastic material. Only we'll discuss time, independent material, where if you are shearing at constant shear rate, okay, it should not change with time, right? Now, when you have apply shear at ramp, again, same curve, it's an interpretation of the same curve, right? Newtonian constant viscosity, you have increasing or you have decreasing, right? Now, the viscosity is just one rheological function. The other one is that let's say you have, means to compute the stresses. So this is the stress tensor, okay? This is the stress, all the 9 component of stress tensor, yeah? Diagonal part and off diagonal part. In Newtonian fluid, okay, the diagonal part, right? They all will be equal. Okay, that means the difference of 1 minus 2 will be 0, 2 minus 3 will be 0. And N1 is that's the difference between sigma 1 1 and sigma 2 2, right? Is first normal stress difference. N2 is sigma 2 2 minus 3 3. Here 1 is the flow direction, right? 2 is the gradient direction, and third is the vorticity direction, right? See, flow direction, gradient direction, and vorticity direction, right? Okay. So in Newtonian fluid, both N1 and N2 are zero. So N1 and N2 are also rheological properties. Okay. But for non-Newtonian fluid, they are non-zero. Okay. And because of this, okay, what it means? It simply says the Newtonian fluids are isotropic, right? Okay. There is no, difference in the direction, right? But for non-Newtonian fluid, the stresses are anisotropy. That means there may be cases where stresses are more along one direction if you try to shear it and less in the other direction, right? And depending on N1 and N2, there are various classes of materials. And because of these non-zero N1 and N2, non-Newtonian fluid exhibit wide variety of properties, like you have dye swell, okay, and siphoning effect, okay, Weizen effect, and so on. Okay. So this is also important when we talk about suspension, because suspension in general are non-Newtonian fluid. Okay, if you have particularly dense suspension. Okay, so yeah. Now coming to the classification of suspension, solid and liquid. Okay, either you can have dilute, that means the volume fraction of the particle is so low, right, that the interparticle distance lambda is much larger than your particle radius A, right? That's one measure. Other is classification is that the volume fraction, okay, the volume of particle, percentage volume of particle to the whole, suspension is less than 5%. Okay. These are dilute. For dilute case, you can, assume that this particle is very far away from other. So as if that this is alone in the, fluid, and you can combine the, extra stresses for all these particles. So Einstein, used single particle, you know, expression for stresses, and calculated that for the suspension in dilute limit, you will have suspension viscosity will be 1 plus 2.5 times the volume fraction, okay, of the viscosity of the fluid in which it is dispersed. So these were analytical, analytically you can determine. For semi-dilute, 5 to 10%, where your lambda interparticle distance is of the order of the particle size. Bachelor and Green, okay, sorry. Bachelor and Green consider two-body interaction and semi-analytical formula. So these are based on method of reflection, because you'll have interaction. This particle will disturb this and so on. Again, this will disturb this and so on. So using analytical semi-analytical approach, Bachelor and Green also gave the formula for semi-dilute, where you can see, right, the extra term phi square, which is proportional to phi square, they have added. Okay. But beyond that, there is no, you can, three particle, solution is not available. Okay. So there is no analytical or semi-analytical formula to predict viscosity, of the dense suspension, where you will have particle volume fraction greater than 10%. Okay. And interparticle distance will be less than the particle radius. Okay. Yeah. Okay. But these are experimental data. So you can see that there are various kind of suspension. So particle volume fraction plotted as eta r. Eta r is the relative viscosity. That is viscosity of suspension divided by viscosity of fluid. Plotted for various kind. Okay. And again, you can see for dilute, you have linear, right? So you have fairly predicted by Einstein. For semi-dilute, slight phi square dependence will be there, right? So it is predicted by Bachelor and Green formula. And for concentrated, you have no way but to fit it. So Kraeger fitted, Kraeger fitted, the experimental data and came out with this kind of curve, right? Krieger and later modified by Daugherty. So it's called Krieger curve, right? That viscosity of suspension will be function of concentration, right? It is eta 0 times 1 minus phi by phi m. Phi m is the maximum flowing packing fraction, okay? The maximum how much you can pack and still flow, okay? And you can see the right, it's diverging, okay? So phi m for, random packing of monodisperse is 0.63. So it goes infinity. That means you cannot flow anymore. It behaves like solid, okay? So now our, goal is that, okay, we cannot have, analytical, okay, for dense suspension, right? Can be computed numerically, right? Can be compute viscosity and N1 and N2 for the dense suspension, okay? Experiment, of course, we can do, but, again, experiments need more time, okay? Also, you can, have limitation of visualization, right? In simulation, you can visualize deformation, okay, the stresses, rate of strain, and also how the particles are being, arranged, okay, as the time progresses. So microstructure and rheology, coupling you can understand better if you are carrying out simulation. Otherwise, for experiment, it is limited only when you have dilute or when you have transparent system. So, okay, that's the aim of this lecture is that how do we compute the rheology of dense suspension. Am I visible? Am I audible or lost contact?
Yes, sir, you are audible,
Yes,
sir.
audible, sir.
Okay. Yeah.
Yes, sir. Yes, sir.
Good. Yeah. Periodically, I'll keep asking. Okay. Now coming to our formulation for the dense, okay, particle suspension rheology. Now I told you it builds from the single particle equation, and we assume that the Stokes law is valid. Okay. And we will see, okay, what are the implication of Stokes law. Okay. Now, Navier-Stokes equation, okay, for incompressible fluid is this is your continuity equation, mass balance, and this is the momentum balance. We all know that, right? Again, it is in initial notation, right? Those who are, okay, not familiar, you kindly read any book like GK Bachelor Introduction to Fluid Mechanics. So this is del J Uj, basically J means repeated. So this will be del Ux by del X, and JJ repeated means summation del Uy by del Y plus del Uz by del Z is equal to 0. This is the same thing what you write, okay, in conventional notation, what we write in initial notation. Again, okay, this is the momentum equation, okay, storage part, convective transport of momentum, right, pressure gradient, and this is the diffusive flux of momentum, right, standard. Now, if you make it dimensionless, right, you make it dimensionless, choose variable like length scale. Either you can choose, let's say length scale, you can choose diameter or, okay, or if you have pi flow, you can choose, whatever, okay, h, some length scale you can choose. Similarly, you can choose velocity. Here you can choose average velocity, right? These are the velocity scale. So you scale your, okay, with length scale, velocity, typical velocity, right? And from length scale and velocity scale, you will have dimensionless time scale, right? Star means dimensionless. So if you substitute all these into these two equations, the continuity equation in dimensionless form remains similar in nature, but momentum equation, this equation in dimensionless form, okay, becomes this, okay, right? And okay, in Stokes flow, the dominant part will be the viscous part. So we divide by the mu u by L square, which is multiplying the, okay, del square ui, right? So if you divide by this, okay, you will, okay, have this modified equation, right? You'll have this equation. And the pressure scaling will also automatically come. So pressure will be, see, pressure is also stress, right? So pressure will be your dimensional pressure divided by some scale, pressure scale. Here it is viscous scale. So pressure is what? Is also stress, force per unit area. And viscous force is what? Viscosity times velocity gradient. Okay. And velocity gradient is y, u by L, right? This same thing as this, right? So now again, you see nice equation comes, okay, and you can easily identify this is your Reynolds number, right? This is a Reynolds number. Okay. Now, if your Reynolds number is much less than 1, this is a particle Reynolds number. Okay. If or in case of otherwise, if it is a tube flow, it will be okay, flow Reynolds number. Now, if Reynolds number is much less than 1, that means you are multiplying left hand side term with a very small quantity. So whole term will go to 0, right? For LE, this whole term will go to 0. For RE less than, much less than 1. So all you will be left is this. So your, okay, continuity equation is this and momentum equation is this. These two equations are called Stokes equation. As you can see, this equation is non-linear. Non-linear because uj, right? Okay. Whole thing drops. So non-linearity you are dropping because of the low Reynolds number. So now this becomes your linear equation. Linear equation you can have solution. It's okay, second order, okay, linear partial differential equation. And what are K? So you can see not only linear, it is also independent of time because the RE small number you are multiplying, even the delta T term goes to 0. So you should not confuse that Stokes, is K. The time is dropping because no, it's because Reynolds number is small, right? So as long as Reynolds number is small, all the flow will have, okay, independent of time. There is no time, okay, in the Stokes equation. And the consequence of that is the property of Stokes equation also follows certain, like they will be reversible and superposition. Reversible means, okay, here means velocity will be related to force. Okay. So if you reverse force, velocity will reverse and vice versa. Because of that, you can have superposition of solution. That means if x1, x2 are two solution, then lambda x1 plus lambda x2 is also solution. What is in implication for the, particulate flow? Let's say you have a particle which is moving also and which is rotating also, right? So this is a complex problem. You can break into one problem in which it is only rotating plus its solution in which only it is translating. So you can, because of linearity, you can simplify complex problem into very small sub problem, which you can easily, solve, right? One of this, which you would have studied in your UG class, transport phenomena, is, velocity field due to a translating sphere and forces also a translating sphere. Same way, you can also find out torque on a rotating sphere. Same way, you can also find out if you are shearing, okay, if your particle is being sheared, right? So if you have shearing motion and you put a particle in, okay, rate of deformation field, you can also compute it as long as it is simple single particle and as long as it is following the Stokes equation. Now from that we can build on the multi-particle system. Okay, so what multi-particle computational rheology we will develop is for Stokesian suspension, right? That's the limitation. Of course, you can also add finite inertia term, but then solution will change, more complexity will come. What do we mean by Stokesian suspension? We are talking now about particle. So the particle Reynolds number, which is density times shear rate times a square. A is the particle radius. Okay, divided by eta is the viscosity of the fluid. Is very small. Peclet number. Okay, right. Again, Stokesian suspension can be Brownian or can be non-Brownian. Peclet number is the ratio of, okay, convective force to the diffusive force, right? Okay, or momentum diffusivity to the thermal diffusivity, which is K for single particle KT by 6 pi mu, okay, A, right? Okay. And momentum is gamma dot A square, right? So this is a Peclet number. So if is much larger, it's non-Brownian. Is much less than 1, it is Brownian. Okay. So there is no limitation on this. You can have for any Peclet number, but limitation is that the Reynolds number should be much less than 1. Okay. Now let us start, okay, building for the single particle. Let's say, okay, this problem which you have already discussed in your UG class. You have a particle which is moving with you and at a distance x, here you have ui. This is the xi, this is the position of the particle, and the velocity. Ui means you'll have, it's the same as u. This is same as u vector, right? In initial notation, we I. Okay. So what will be the velocity field at this point, okay, which is at the distance xi or distance r from the center of this particle? Okay. Yeah. Now we'll not go into the details, right, of solution. Okay. You can, build on, okay, either using Green's function or, okay, a spherical harmonic solution. So solution field that ui at this point is this, okay, right? And p, because Stokes equation, right? What is the equation? Your equation is del p by del xi is equal to mu del 2 ui by del xi square, right? So p and u are variable, right? I mean, okay, uh, a dependent variable, and this is the solution. Ui is this, the velocity field is this, and pressure field is this. Okay. Uh, those, okay, who want to go deep, you just look into any book like bachelor GK bachelor introduction to fluid dynamics, or NPTEL lecture by Professor V Kumran. I think in morning he would have taken your lecture, right? Was there lecture in the morning? What
Yes,
was
sir.
his
Yes, sir. Yes.
what was his lecture on?
Yes, sir.
Hello.
Hello,
Yes, sir.
am I audible?
Yes, sir. You are audible.
Voice is clear or I need to speak louder?
No, no, no. Voice is clear, sir.
Why? No, I'm asking, was there any lecture by Professor Kumar in the morning?
Yes, sir. Yes, sir. Topic
It
was
was
multi-scale modeling of laminar
laminar
mesophases.
Okay, okay, fine. Yeah, so he has an NPTEL lecture which nicely, describes how to get your solution, of Stokes equation, right? So I'll not go
Yes, yes,
into,
yes.
yeah, you
Definitely,
can
definitely.
record. Now, once you have velocity and pressure field, okay, you can easily find the stress, right? Because I told you stress, right? Viscous stress is what? Viscosity times, okay, the symmetric part of velocity gradient tensor, isn't it? 2 mu times the symmetric part. This is the symmetric part, right? So once you have velocity, take its, okay, gradient, you get this thing and this thing. It's a transpose, right? Also, okay, the forces is the total forces. So it's not only viscous part, the pressure also contributes. So it's the capital T is the bulk stress, which is minus P Ni is the Ni is the unit normal, right? Is the N is the unit vector plus tau I k n k. Right. Again, n is the unit normal. Right. And once you have this, take, okay, gradient, you'll get this. Okay, it's transpose, you'll get this. Right. So once you put it, you get tau I, the viscous stress. T is here and this is here. You substitute and you do the integration. Right. Again, these are some, okay, expansion. Again, you can see it's nothing. You have to use chain rule, right? Okay. See, this is one, so one component, one, two, three. So chain rule will give three component, three plus four, four here also four, eight, right? So you'll see eight part, one, two, three, four, five, six, seven, eight. So using chain rule, okay, of differentiation, you have got this, right? Okay, and you put it, and then you carry it out this, okay, integration. You can easily show that the force on this moving particle is 6 pi, a drag force is 6 pi mu r ui. Okay, that's your Stokes drag law, right? Same way, you can also solve this problem, right? So this problem, little bit detail I told you. Same way, okay, of course, you'll have to use boundary condition. For translating boundary condition is that at the surface, velocity of fluid is velocity of particle. Far away, velocity of fluid is that of undisturbed. Okay, same way you'll have rotating sphere. Okay, with same Stokes equation with boundary condition that at the surface particle velocity is what? Okay, omega cross r, or a is the particle region, far away undisturbed. Okay, so you can carry it out the similar way and you can find out torque. So this will be torque on a rotating sphere, which is 8 pi mu r q. R is the radius, omega I is the, okay, rate of, okay, vorticity of the your particle. Okay, uh, yeah, same way you can also have solved this problem, right? When you have a particle which is in a rate of strain field, right? That means you have a rate of strain field and you substitute a particle, put a particle, right, of radius r. What will be the stresses, right? And stresslet is the is the symmetric part of the first moment. So it's not the total, right? So this is your stress, and xj is the distance of any point from the center, right? So this is the first moment of stress. So symmetric part is called stresslet. This is stresslet. So stresslet also same way you can find out a solution, and which will be, if you have imposed eij, it will be this. So all these are coefficient, right? 8 pi mu rq, 20 by 3 pi rq, and in this case 6 pi mu r. Okay, right? In this relates force to velocity, torque to angular velocity, stresslet to the rate of strain. These two are vector, but this is tensor. So that's why this second order tensor is relating to a second order tensor, right? Okay. Okay. So we have now fundamental solution or analytical solution for various cases. Now, suppose we have to calculate, viscosity of dilute suspension, right? So this is the explanation how Einstein arrived at this formula, where viscosity of dilute suspension is viscosity of fluid times 1 plus phi 5 phi by 2. Okay, is simply basically averaging stresses. So Einstein also assumes very dilute. That means it assumes that these particles are moving independently, as if these other neighboring particle has no influence, on the the particle velocity or particle stresses. So all you have to do is that in a dilute you have many particles, so you'll have to average, right? So this is nothing but averaging. Okay, so you have average stresses, right? And we know that right, this is the formula. Stress is isotopic pressure part plus the viscous, right? So now you just have to average over all the particle, right? So let's say you have to do averaging over all the particles which are there in the suspension, right? And when you say averaging over whole suspension, suspension comprises of particle plus fluid. So you can split this average over the whole suspension as some manipulation. First you do what you do, you add this term and you subtract this term. See, we have added, this term is added and this term is subtracted, right? Okay, so what you are left is the original term. Okay, why we are doing it will be clear, right? Now this term, as you can see, right, this is the definition of volume average, right? Mu is constant because you have suspension in Newtonian fluid. So this is becomes your average rate of strain, right? So this part is this. Okay, second part you break into two. Suspension means break into fluid part and particle part, right? Isn't it? And for the fluid, what you have in the for the fluid, your viscous stress is what? For fluid, your viscous stress is simply 2 mu Eij. So this term goes zero, right? For averaging, because mu Ij, tau mu Ij is 2 mu Ij. This remains. That means average on the particle remains. So what we have reduced? We have reduced from integral over whole suspension to integral over particle, because we know the solution of the particle, right? We don't know the detailed solution of the fluid flow field due to many particles. So now it is this. Now there are many particles, right? So if there are n particle, you can have, so volume integral over many particle is n by v volume integral over one particle. Why? Because again all particles are similar, right? It's dilute limit. So this is all particle. Now this is one particle, but then this n comes, right? And you can show that n by v, n is number of particle, v is the volume, isn't it? Now you can show that this what is the particle volume fraction? Phi is, if you have, is the volume of particle, if you have n particle, n into 4 by 3 pi rq. That means the volume of particle divided total volume of suspension, right? That's the definition of the volume fraction. Particle volume fraction is the volume of particle, that is n number of particle times the volume of one particle, 4 by 3 pi rq, divide the whole volume of suspension. So from here, N by V will be phi by 4 by 3. Okay, this term comes. And again, volume of one particle. Now we usually know volume integral is difficult, okay, because okay, when the drag force is mostly caused by the surfaces, right? So we convert this volume integral to surface integral using another manipulation. Consider this, okay, gradient of tau IL, okay, xj by del xl. X is the okay with which you are taking the gradient. Using chain rule, you can write like this, okay, right? And what okay we have is this, okay, tau ij plus xj this. And what is tau il del xl? What is this? This is nothing but your del dot tau, right? In it. And what is this? If there are force-free particle, del dot tau is zero. That's your momentum equation. Okay. This is a momentum equation. So this term goes to zero. So tau ij you can also express this. This helps us to convert volume integral to surface integral, right? So now using this, so you can write, okay, the tau ij which was appearing here, we can write del tau ij il xj by del xl, right? Now we can use the divergence theorem. Okay, so if you have volume integral of, okay, divergence of certain quantity, that becomes surface integral over the surface of Tjl xj, right? Okay, Nj is the unit normal on the surface, right? This we can easily handle. We can easily integrate on the surface of the particle, right? So that's all is that. Now, okay, all you have to do this integration. This solution is available, right? So there's the in a rate of straining field, okay, there's the solution. Well, this is the velocity field. Once you know velocity field, you know that stress is basically 2 mu times the symmetric part of velocity gradient. So you can calculate gradient, right? Right. So you do substitute this and it comes to be this. Okay. Right. That means the integral surface integral of Nj TIL xj is 20 by 3 pi RQ mu EIJ. Okay. So this if you substitute in this equation, you get the expression for the average stress. Average viscous stress in the suspension is equal to 2 mu Ij plus 5 mu Eij, right? Okay. You have to substitute here in this one. So this becomes 2 mu this, right? Eij. And you can see, right? Okay, this is the same way, right? If you relate it, okay, if you relate tau was 2 mu for Newtonian without particle, if tau was 2 mu e, we can also rearrange this. So 2 mu this, okay? So now you see mu effective is basically this, right? 2 is there, though this becomes mu effective. So mu effective, that means suspension viscosity is mu times 1 plus 5 phi by 2. Okay. This is the viscosity of suspension. Clear? Am I audible?
Yes, sir, you are audible.
Okay. How much time I have? Okay. Now, yeah, that's the most part you have understood, right? This is the okay, and everything is built on that. Now coming to dense suspension, right? Where you have many particle, right? Where you cannot have the assumption of dilute, right? For single particle in a shear, right? So this is for single particle. You can relate force, torque, and stress rate, right? So this we've derived, right? Force was 6 pi mu AU. Now it may happen that the fluid has the fluid velocity is this far away from the particle, and UP is your particle velocity, right? UP is particle, right? Same way you can have a disturbance velocity field. E is the imposed, okay? Infinity means far field. Omega is the vorticity. Maybe you are simulating in a rotating system where itself your flow has some rotating velocity field. Okay, right. So you can relate force to the velocity, torque to the angular velocity, and the stress rate to the rate of deformation. Now, why there is no EP, right? Why there is no EP0? Why? Because these are solid particles, right? You cannot deform. You cannot deform a solid particle. It will not support deformation. That's why EP is zero. EP has to be zero. right? But if you are simulating droplets and other, soft particles, then EP will be there, right? Then it becomes more complicated. So for single particle, it's fine, right? So this is called K, force and torque and stresses, okay, and this is called resistance metric, right? So this is R. So you can say F is equal to R, and this is the velocity vector, all translational, rotational, right? But for multiple particle, now you come to multiple particle, right? Again, because of linearity, Stokes law is valid. So you see, force is linear with velocity. This is the K, the coefficient, right? For single particle, it just depends on the viscosity and the size of particle. As you can see, there's only two things. But if you have multiple particle, right, then suspension, then all the relative, distance between two particle will matter. So this R becomes very complicated, right? It becomes K, a relative position dependent tensor. Okay. So if you can calculate for multi-particle system this, okay, the relation still remains same, that the force is linearly proportional to the viscosity or velocity, sorry. Okay. The challenges in computing, this, okay, is this, that you have long range interaction. What do you mean by long range? Okay. That means if you are moving a particle, the velocity field decays very, slowly. As you can see, it is 1 over r. See, RQ, that means if you have very far, RQ will be almost 0, R4 0, R5 0. But the velocity field, K, for Stokes flow is 1 over R. That means even 10 particle radius, 1 by 10 is 0.1, 10% is not 0. It's not small. So this is a long range interaction. That means you have to consider the full solution, right? You cannot just truncate in you can say that only near field interaction or lubrication I can handle. No, you have to solve the many body problem with long interaction. Many body, what it means, Einstein assumed that the particles, one particle is not disturbing the other, this one is not disturbing this, right, and this. But actual dense suspension, if you move this particle, this velocity field here disturbed, this will have some forces, this moves, this will have, then come back. So there will be multiple reflection. So many hydrodynamic interaction, I told you, there is no analytical solution, right? That's the challenge for all problem, whether it's a planetary body or whether it is the suspension hydrodynamic. Many body problem has not been solved. Okay, people use some approximation and solution which is fairly good enough. So that's why the challenge is how to compute many body interaction. Also, the particle can be not only far all the time, they can be close, very close, so that you'll have lubrication. Lubrications are two body forces, right? So you can have squeeze motion, you can have shearing motion, you can have twist, one particle rotating this way, other this way, there will be torque, on all sort of complications will come. But fortunately for two body, we have analytical solution, right? So that's not a problem. The problem is the many body. We do not have analytical solution for three sphere or more than three sphere. For two, we have semi-analytical solution, right? And unfortunately for dense, we have to consider many body. So of course, other than hydrodynamic, okay, you can also have non-hydrodynamic, like repulsive forces, attractive if they are charged particle, frictional forces if they are rubbing each other, and so on. Okay. So how the Stokesian dynamics, is the simulation for computing rheology of dense suspension is basically okay, is built on. Okay, so you can study this paper. It's a review paper, very nicely written. Okay, okay, annual review of fluid mechanics. Okay, okay. So basically, it builds from again Stokes equation solution which we have derived, right? So this is the Stokes solution will not go either your particle is stationary and you have fluid field, or the vice versa. The fluid is stationary and moving the particle. It's just a reversible problem, right? The solution will be just minus of that in that case. Yeah. So we have harmonic solution which I also discussed this, right? Now let's say that how can we use it for multiple particle system, right? So this solution, let's say we have this one, and we know that the drag force is this, right? Drag force is this, right? That means U infinity or UP will be what, right? Will be Fk divided by 6 pi mu A, right? Or if the particle is moving, right? If the particle is moving UP, then UP will be F by 6 pi mu A. You substitute this into this, wherever you have, okay, this one. You substitute this, then you will get this one, okay? Yeah, sorry. You will get this one, okay? Right. It says the sum of K FH plus Fe. FH is hydrodynamic, Fe is external. These are, force-free particle, right? So sum of this has to be 0. So Fe is just minus FH. Okay. Now, in this velocity field, okay, if you substitute this, what it becomes? It says that if you know the force, okay, field, okay, which you have applied, right? Let's say point force. Then the velocity field is this. Okay. Now A square is there, okay. But if A square goes to 0, that means the particles are very tiny. Then what will happen? The whole second term this goes to 0. So as A goes to 0, this whole term goes to 0. Okay, right? So as you shrink it, whole term goes to 0. Now your velocity disturbance field is this due to point force. That means in a fluid field, if I just apply some force disturbance here, right? Fe, velocity field at some x distance will be this, right? And you see this is k proportional to the point force, and this k is called Stokes limit, right? Okay, and this is called Oseen tensor. Oseen tensor. Okay, so what it says that the disturbance velocity due to point force is proportional to the point force itself. So Stokesian dynamics, and okay, it's known as Stokeslet also. Stokesian dynamics is built from a point force. That means it constructs a particle by distributing point force. Okay, a small tiny is creating some disturbance. You can distribute this tiny force field on the sphere. They all will create disturbance at some certain point, right? So it's built from the point force solution because point force solution was straightforward, right? The Stokes limit. This is the Stokes limit. So if you have multiple point force, for example, okay, just to demonstrate, you just sum over that this disturbance velocity field at this point, okay, this is the x alpha, okay, right? At this point is due to all, due to this. So you'll have to just sum over the disturbance, right? They are additive, right? Velocity disturbance are additive in nature. Now, if you have, particle, you can distribute. So distribution of, Stokes limit, if you distribute on a spherical surface, you create spherical particle. You can also distribute such a way you can create ellipsoidal or, any, regular shape of particle also can be created. So now you can say that the disturbance velocity field due to a sphere will be, right? If it is a regular distribution, this summation you can express as surface integral, right? Right. So this is the velocity field due to the point force. This is the what was there in the fluid, right? Okay, far field, and then you integrate the whole surface, right? And this one, what is force, right? Force is basically stress into area, right? And this will be at a function, right? This is not y multiplication. This is simply this is y, right? And this ds is y. That means on particular y. What is y? See, this is your from the surface, okay, this point, this is your y, okay, right? So this is your stress into area is the force, right? And this is your Stokes limit. Okay? So you just have to integrate. Okay, you will get the disturbance due to this is the disturbance velocity field. This is a u dash disturbance. If there was no particle, this was velocity. Now force, you have created a particle or you have created a disturbance. This is the disturbance velocity field. So if you have same way, if you have many two particle, you just this plus this two. If you have many particle, you have to sum over all the n particle. That's all. Okay. This is the basics of the suction dynamics. Now, okay, you can once you can have the disturbance velocity field due to all these particle at a certain point. This point is integration and summation, of course, overall. Okay, on this. What Stokesian dynamics does is that it expands this in Taylor series, right? Taylor series. Okay, about where? About center of the particle. This is the center of the particle. Why it's called multiple? Because for this distribution of Stokeslet, it expands about this. For this one, it expands about this. So there are multiple. There is no single pole of expansion. There are multiple. So you know the Taylor series, right? Fx plus okay, isn't it y okay into f dash x, right? And so on. And it takes only two terms, first and the second term, and it neglects because the other term will be 1 over rq and so on. They will be small. Okay. But if you want more accuracy, you have to take higher order term, but then it becomes more computationally intensive. What Stokesian dynamics does okay, it consider only two term, right? It's simple. The vector, okay, right, for the, scalar field, x plus k, delta x is what? Is fx plus delta x f dash x, right? It's the same thing. This is the f dash of this Gaussian tensor, right? Okay. So this is called zeroth moment, right? This term, okay, and this is called first moment, okay, where delta x multiply your f dash x, right? Okay. Um, so as you can see, right, okay, this is a vector and this will be tensor because you are taking derivative, right? Mind it is not okay, grade, it's a derivative, right, of a vector, so it becomes a tensor. So second term is a basically it's a second order tensor, just like you had a stress tensor, okay. And it again has, you can break into symmetric part, antisymmetric part. Symmetric part is stresslet and antisymmetric part results to the torque on the particle, right? Okay. So this is the first moment, okay, the second term of the Taylor series, right? Okay. The first moment is a second order tensor. It has symmetric part and antisymmetric part. And faction K related it that the disturbance velocity field. This is the disturbance velocity field. That is how much disturbance this the Stokeslet or the particles are created. This is the disturbance in angular velocity. This is the disturbance in the rate of deformation. Okay. Of course, okay. Again, EP is zero because you cannot deform particle. But if the particles are soft, then this will not be zero. This is zero for rigid and will not be zero for soft particle. Okay. So faction related that if you know the disturbance velocity field, right? This is the velocity of particle relative to the fluid velocity. You can relate to the force and you can relate to the disturbance velocity field, right? This is the gradient of velocity and this is the deformation, okay, EIJ, right? Okay. So now if you substitute the Stokeslet, if you substitute this into this, okay, all the disturbance, right? Same way, just like we had, okay, this one for the translational velocity, you can also have disturbance for the angular velocity, and you can also have disturbance in the deformation of the field due to the particle, okay? So if you substitute it, you can, relate it in a very nice form where this is the, translational velocity, angular velocity, and is the rate of deformation tensor to the force, torque, and stress rate on the particle. And this is the, okay, M is called mobility matrix, right? It's a, okay, big matrix, okay, depends on the, what is the order, okay, and it has different component, right? As you can see how many it will have, okay. It will have A, B, G. Again, these are not scalar. I mean, they are not constant. They can be order like first order, second order, third order, fourth order. So there will be A which will relate U to F. B will relate U to torque. G will relate velocity to the stresslet. Okay. Similarly, B its transpose will relate angular velocity to the force. This will relate C. That means rate of deformation to the torque. And this will relate, the M will relate this two. Okay. Rate of deformation to the stresslet. Okay. All these has been nicely, shown how do you compute it, its component in a book, Micro Hydrodynamics. Okay. So this is the very detailed book. If you want to learn Stokesian dynamics, you should, read this book. It's a very nice book. So, okay, also the paper of Dulowski and Brady gives fairly detail, right? That was for for any particle alpha. Now you have multiple particle, right? So this particle, you have this particle, this will have three component, yes? So it have three velocity component and it will have three angular velocity component also, right? And it will have, okay, S, which is 9 component, right? So this is the first particle, second particle, third particle. Each will have, right? So if there are n particle in system, what is the size of this matrix? You'll have n translational velocity, right? N will be U for n particle. 3n, sorry, 3n because 3 component. 3n will be angular velocity of particle, right? And how will be? 1 will have 9, right? Isn't it? So for n will have 9n. S is right. S or E is the second order. It's 9 component, but they are symmetric triplet, right? S or E, but they are symmetric and triplet, so it reduces to 5 component. So in 3D, okay, if you take advantage of symmetric triplet, 3, 3, and 5, 11. So this will be 11n by 11n. This is the size of matrix, right? And this also has to be, 11n. Sorry. This has to be 11n. This has to be 11n. Okay. Otherwise, if you take all component, no need, because why don't you take advantage of symmetry in nature? Otherwise, it will be more. But you can reduce it to 11n by 11n at maximum. Right. So if you n is large, it's fairly big system, right? And you see all these are pairwise. That means the one with one, one with two, one with three. So this grand mobility matrix is found pairwise. That means this disturbance created, okay, by this particle on this and so on, right? So the pairwise, okay, mobility matrix function, and these coefficients, okay, are basically dependent on relative position. So you want to know coefficient any between 1 and 2, you should know what is the distance, right? What is the distance Rij between this? Of course, they are vector form, so you should also know the, okay, the vector, which way it is directing, okay, and so on. But then these are fairly detailed, okay? It's just coming from those coefficients, right? Single particle, the diagonal part, 6 pi mu for forces, 8 pi mu for torque, and 20 by 3 for the stress rate, okay, pi mu r cube. So fairly straightforward, okay? They are tabulated. Reverse of this is resistance matrix, right? So mobility, if you know forces, then you can calculate velocity if you know m, right? But many problem, you, okay, no forces and you have to calculate velocity. Then you'll have to solve inverse problem. That's called resistance, which is inverse. Where if you know the velocity, okay, all translational, angular, and rate of strain, you can calculate force, torque, and stress rate, right? So this is R is, okay, there it was M, this is R, right? And R you can get is inverse of N, right? Resistance matrix you can get by inverting the mobility matrix. Is it okay? Am I audible or lost connection?
No. So it's audible.
Okay, I think, yeah. Yeah, maybe we'll finish in some more time. Of course, in 1 hour it's difficult because it's a whole course actually.
Yes, sir.
Uh,
Yes, sir. I know.
but maybe I'll take 10 more minutes. Okay, is it
Okay,
okay
okay. Okay, sir. No
to
problem.
wind up?
Hmm.
Now, I told you, okay, that these mobility matrix, okay, they are computed, okay, why? They are based on the multiple expansion, right? Taylor series. And in Taylor series, we neglected higher order term, right? These higher order term, okay, become more and more important when the particles are coming closer. When the particles are coming closer, right? That means 1 over r cube will also not be small. That means you'll have to consider even those terms. Yeah, for these widely separated, R is very large, so 1 over RQ you can neglect. But when they're close, you cannot neglect. But while formulating mobility matrix, we neglected in Taylor series. We consider only zeroth moment and first moment. We neglected, okay, higher order term in Taylor series. Because of that, okay, this does not consider the particle close by. So close by particle we can add. Fortunately, when the particle is close, right, two body interaction is important compared to three body, because third particle will, the forces, three body forces will be very small compared to these two, because lubrication will be, these two will be so strong, it will be, let's say, 100, then this will be only 1. So you can neglect 1 compared to 100. That means you consider only two body. That's why we can add two body lubrication when the particle come closer. So when the particle are far, mobility works. When the particle, because these are dynamic, when the particle come close, you have to form this two body. Okay. And fortunately, two body lubrication problems are, you have analytical solution. So again, all this comes from those analytical solution of two particle, translating, two particle, in shear, two particle rotating, all sort of various combination, these solutions are there. Okay. So you add on, these. Okay. So what is the, method of Stokesian dynamics? You first, form a mobility matrix which relate velocity to the forces, right? And this pairwise, one with two, okay, and so on that. And then you invert it, right? Invert you, this is the mobility formulation, and this is your resistance formulation, right? But when, okay, important thing is that, see, this is what? Far field, right? And this is two body because of Taylor series truncation. So this is far field two body. Okay. Now Dulowski figure it out. Okay. You read this paper, Dulowski and Brady. They figured out that if you invert a matrix, if you invert two body matrix, means one with two, one with three, and so on. This two body, two particles at a time, and you form a big matrix for all the n particle. But when you invert it, it captures many body interaction. Okay, and you can easily show it that when you calculate inverse of a matrix, right, all those terms are taken into account, right, and it comes out that it captures the many body. So the method is that you form two body many body problem with two, okay, using two particle at a time. Of course, it is approximate far field. Invert it, so this now captures many body, but it is far field. You add lubrication. Now many body also has two body, so two body is added twice, so you subtract once, not to avoid double counting. So that's the whole procedure. Make a for n particle, make a mobility matrix, invert the mobility matrix, and form a grand mobility resistance by invert plus R2 body. And to avoid two body, especially far field, you subtract this. Once you know this R, that's all. Okay, you can find out many rheological, okay, properties or average property of suspension. Okay, so you see it does, okay, yeah, pairwise and then do. Once you have R, okay, you can use solve language equation. Then it's just like a molecular dynamic simulation, right? You know forces, you can, okay, calculate velocity, can update the position. Now language equation, is just Newton's second law. That's mass times acceleration is sum of forces, hydrodynamic, Brownian, or any external forces. Okay, right? Hydrodynamic force is what you have calculated. This, right? Okay, this is hydrodynamic force, F. Okay, right? So if you have, low Reynolds number, this goes to 0. Why? Re less than 1. There is no acceleration, right? Particles are moving very slow, creeping flow. Then sum of forces is 0, right? And hydrodynamic force we calculated. It is just RFU dot U minus U infinity. Okay, you can also expand it for other component. So U is not, okay, just to avoid, complete writing big matrix. U is a vector of velocity translation as well as rotational velocity, right? And F is the vector of forces as well as torque on the particle, right? Okay, interparticle forces, you can add, okay, there are some cases where you'll have some charges, so you can have DLVO forces also. So this is a DLVO forces, okay, if you have colloidal system. Okay, now once you know this, you can solve this equation. So this is, AX is equal to B, AX is equal to B, A matrix, right? If you want to know the velocity, you just solve. Okay, so, okay, velocity field solution is this, RFU inverse into FE plus RFE dot P. And FE, right? And all these are configuration dependent matrix. This you are imposing. So you will solve the velocity field. Once you know velocity, that means this particle velocity now you have calculated, right? So now you can move it. So where the particle will move, it will move by a u times delta t. Delta t is time step that you fix it. So afterwards, once you calculate this, afterward it's molecular dynamic simulation. Same. Start with the initial configuration, right? Calculate R, find U, then you integrate it to find where the particle, how much displacement it has, move to a new location. Again, you do repeating. Again, new forces and so on. Okay. So as we see that the resistance matrix is very important. Okay. And once you know resistance, it solves all your problem. Right. For example, you can show in sedimentation problem, you want to study sedimentation of suspension, right? Average sedimentation velocity is Rf inverse dot Fg. Fg is the gravitational force vector. Okay. Flow through porous media, right? Okay. N is number of particles in porous media. Porous media is also suspension. Only thing is the particles are fixed, only fluid is moving. The permeability tensor, inverse of permeability tensor is number of particles divided by volume, averaging volume time average of RFU in that volume. They will give you permeability. You can solve rheology. Okay. The whole K average suspension stress K is the K. Pi is the particle pressure, and this is the viscous part of the due to fluid. And this are different component of stresslet. Stresslet, you know, we have computed hydrodynamic K due to interparticle and the Brownian forces, right? And again, these components are related on these R. If you know R, the resistance tensor, you can calculate the component of stressless due to hydrodynamic, interparticle and Brownian forces. You're solving diffusion problem, diffusion tensor. If you know RFU, you know this. In microstructure, I told you, okay, how do you evolve? So all is about finding this, okay, right? F is R, okay, this big, okay, F force is this, okay, into this, not you. It's all about R, finding R, and what R depends? It depends on position of the particle, and of course, coefficient will be depends on the solution, Stokes solution. Okay. So this is okay, what okay. Bonded one, I think due to lack of time, I will just skip it. They are easy. These are for the unbounded. That means okay, these are for simulation method where you have particle and which is in a shear field, rate of strain field. It is in this field. Then you can calculate this RF, right? Most of the problem you have bounded, right? That means you have flow in some tube, channel, and so on. The only thing you have to do, you have, in addition, we know this calculate, okay, R for this. Now, when you have wall, then you'll have to calculate particle wall interaction. That's all. You'll have to add particle wall. So that means when the wall is coming, when the particle has come close to the wall, you add it. Fortunately, you can have two body problem when when the wall is close by. Of course, details is little complicated. You can read in this paper. Yeah, you can read. Okay, a paper written by us long ago. Right. How do we add particle wall interaction? Okay, for various fields. So you can simulate. Okay. Of course, I told you that these problems analytically are available. Particle moving near wall, rotating near wall, right? Approaching wall, rotating perpendicular wall, or near the wall but in a shear field. All this you have analytical solution. So you can add it. Only the far field, only this one. Only this one you'll have to compute it, right? By inverting matrix made of particle and the wall. Okay, so think this is the okay, of course it just like any method you have to validate. So there's a validation with other method which are not Stokes dynamics, which are fully resolved, okay, method where you have solving full Stokes equation, okay, not neglecting any term. You see good match is there. Okay, bonded flow, okay, and this is the okay viscosity, relative viscosity against volume fraction. So you see this is the SD simulation and these are experiments. You can see a good match. Of course, scattering will be there as you go very high because at low volume fractions mostly hydrodynamic dominates. So and Stokesian dynamics is able to capture hydrodynamic interaction very well. As you go high, there are a lot of non-hydrodynamic forces, contact forces, friction forces comes. Then unless you modeled correctly, so this was only purely hydrodynamic. To compare with experiment, you'll have to add non-hydrodynamic forces also. And there's a N1, you can also calculate the radial distribution function. You can show why, N1 is non-zero, right? I told you the first normal stress difference. N1 is non-zero and is a function of phi for concentric suspension, right? For Newtonian, N1 is zero. This is zero for Newtonian fluid. So clearly suspension behaves non-Newtonian. You can calculate this. You can explain, right, by seeing the particle distribution, right? You can see that why N1 is positive, because you have more particle in compressional quadrant, less particle. This is the radial distribution function. Okay. Clearly you can relate rheology to microstructure. So all these you can do, which you cannot do with experiment. Okay. Very easily. Again, if you have, okay, very dense, where friction also comes in picture, right? So you can model just like DM. So you can couple Stokesian dynamics with, so you can use SD plus DM. Brownian force is easy, right? Okay. And if you have want to capture shear thinning, then you'll have to use, double layer, okay, repulsive potential, also DL view, right? So with these, actually, you can show, right, the real typical, this is the typical, what we have shown initially, that at low fraction this behaves constant for suspension. But as you go high, okay, and okay, shear also high, then it becomes shear thinning. And at very high shear, it becomes shear thinning. This is typical behavior of suspension. We only proved this one. To do this and this, you will have to include this non-hydrodynamic forces. Okay, which also you can easily couple. So, okay, Stokesian dynamics coupled with DM. This is what, okay, it capturing the, okay, shear thinning behavior. This is also, it's capturing this part, right? You see this part, it is capturing why there is an increase in viscosity. Okay. Of course, correct behavior, capturing requires, a lot of study on actual forces and also very small time step. But qualitative behavior, okay, in different zone, okay, it has been captured. So, as you can see, Stokesian dynamics is very powerful. It is very accurate technique in terms of capturing many body hydrodynamic interaction. I think that's all. Okay. This is the conclusion. Okay. So what is challenging in dense suspension rheology is the many body hydrodynamic interaction, which Stokesian dynamics capture very correctly. Bounded particle wall you can add, and if you have shear thinning, shear thickening rheology, then interparticle becomes important. That you can do with Stokesian dynamics coupled with DM, okay, discrete element, okay, method of simulation. So thank you. If you have question, I can take question.
Okay, participants, now it's time for question answer. If you have a question, you just ask.
Hello, am I audible?
Yeah, a little louder.
Hello, am I audible?
Yeah, tell me.
Yes, so I am Pranil from IIT Guwahati. I
Yeah,
have
yeah.
like
I,
two questions. Firstly, very interesting talk. Sir, first question is related to like one of the last slides that you showed, wherein there
uh,
was, I think, shear thickening, shear thinning behavior, and how you are relating that to Stokesian dynamics. So the
yeah,
question which I had was,
yeah.
here I think the molecular architecture, or say the particle architecture, or the way that these particles are arranging themselves in the fluid. For example, for shear thinning, we see that there
Mhm.
is a layer-like arrangement, and shear
Yes.
thickening, there is cross-linking type of arrangement that we see in
Here
the polymers.
cluster formation,
So
a
how
lot of particle cluster, and there is a friction, coming in play, which prevents the breakage of cluster.
so like for these macroscopic molecular or particle arrangements, how does Stokesian dynamics capture them?
How macroscoping in the what way? Yes, we have seen microstructure. I have not shown it. We can have, a particle position at every time step, and we clearly see that there is this kind of layering when there is a shear thinning, and there was cluster. That means many particles were touching each other when there was shear thickening. So we could relate microstructure to the rheology.
Okay, okay.
That means,
Sir, second,
yeah.
yes,
Go
sir.
ahead.
Uh, Yes, second question was that for active matter suspensions, for example, if I have a bacteria which is growing in a colony, so
Yes.
like there the rheology should be changing from say very dilute wherein I have like very few bacteria from to very dense suspensions wherein the bacteria continuously grow over the time and from colonies. So for
Mhm.
these, what do we need to incorporate in SD simulations to capture such transitions between two asymptotes?
See, as long as the active is concerned, yes, you can model. All you have to is that use some active forces. That means self-propelling forces on the particle, right? Okay, that people have done. So Stokesian dynamics has been used for active particle. But when the particle number is changing, that you cannot do because Stokesian dynamics is for fixed particle. That in your simulation box, the particle remain fixed all the time. You cannot multiply, you cannot capture, multiplication of bacteria. But yes, motion of bacteria, again, people have, used slender body particle also to mimic the bacteria, okay, which is some elongated shape. Also for spherical, so all they have done is they've used some active forces, right? They are, okay, self-propelled forces. So that has been done. You search, Stokesian dynamics for active suspension, you will find many papers.
So for continuously dividing media, are there any approaches which are currently employed, or is this an open area?
No, it's an open. Stokesian dynamics is all Lagrangian. That means we do not solve for velocity field, right? We just use the solution, Stokes solution. Okay. So when you ask, can I get velocity field of the fluid? No, it doesn't give you velocity field of fluid.
Okay.
But
Thank
in indirect way, you can get it. What you can
Okay.
do, you can use Stokesian dynamics for two different sizes of particle. One is very tiny, such that it convex with the fluid, and another is your actual size. So tiny particle will give you velocity field of the fluid, but that becomes, another, completely intensive. But people have done it, for limited number of particles.
Okay. Thank you so much, sir.
Thank you, Pranil. Any other? Hi, Anurag, you are muted. You're speaking, you're saying something? No, Anurag, you're muted.
Okay. Now it's
Ah,
audible.
yeah.
Yeah. So I hope there is no question. If any question, you just quickly ask.
Okay, I'll
Oh,
suggest those who are interested to read the book and review paper by Brady and Bossis. Type stroke. And the good thing is that the MATLAB version of code is available for free. You just type in Google MATLAB Stokesian Dynamics. You will get the code free. Run it for few particle. You will get a feel. Whole code is there. How, resistance matrix is calculated, how it is inverted, how mobility is formed, and how do you integrate in time, and how you see the dynamics of particle. Everything is free. I think some people have also made free the Python version. Those There's an interface, people want to accelerate it by using machine learning. So Python version of Stokesian dynamics is also available. So use that, read the book, Micro Hydrodynamics, read the review paper, Brady and Bossis, and use the